Okay, glycogenesis is the reactions we're going to take a look at in order to store glucose. So in order for storage of glucose, we of course have to be in the fed state. Fed state means insulin in the circulation as our signal that we are in a fed state. This is going to induce the translocation of GLUT4 to the cell surface of skeletal muscle. And now skeletal muscle will have access to the circulating glucose from our meal. The glucose will enter the skeletal muscle, and the first reaction is, as we've seen in glycolysis, is formation of glucose 6-phosphate by the enzyme hexokinase. Now these principles of glycogenesis are the same also in liver, but liver has GLUT2. Glucose will enter the liver through GLUT2 and will also phosphorylate to form glucose 6-phosphate, but with the enzyme glucokinase. Once we have glucose 6-phosphate, down the glycolytic pathway, we are going to isomerize this into glucose 6-phosphate. This is phosphoglucoisomerase. And then, of course, our next reaction is done by our enzyme PFK1. And this is considered the gatekeeper. What do I mean by gatekeeper? This enzyme is the key regulatory enzyme in glycolysis. This will, of course, generate fructose 1,6-bisphosphate using ATP. So the gatekeeper of glycolysis, this enzyme will regulate to determine if we will continue proceeding through glycolysis or if we will inhibit this enzyme, causing an increase in fructose 6-phosphate. What inhibits this enzyme, recall, is high levels of ATP. High levels of ATP indicate in the fed state that we've gone through glycolysis, TCA cycle, oxidative phosphorylation, and recharged the cell. So this is the high energy state of the cell. Once we have all of our ATP made, we can now inhibit PFK1, which will increase the concentration of fructose 6-phosphate because it's not proceeding past this point. Recall the isomerase reaction is readily reversible. So if this concentration builds up, the delta G becomes negative. Free energy change becomes negative in this reverse direction. The hexokinase reaction, of course, is using ATP to phosphorylate glucose, and this reaction, of course, is irreversible. So that means we have an increased concentration in glucose 6-phosphate under these conditions with a high energy charge. At that point is when we can begin glycogen synthesis. So the first step in glycogen synthesis is to take our glucose 6-phosphate and convert this into glucose 1-phosphate. So this is simply moving the phosphate group from carbon 6 to carbon 1. This enzyme is phosphoglucomutase. Recall again that a mutase is just simply moving a phosphate from one carbon to another. Now that we have our glucose 1-phosphate, we have to prepare the molecule for the next reaction, which is in glycogen synthesis. So I like to draw the analogy to a poker game, that if there's a large poker game with a bunch of people, if you as an individual would like to join the poker game, you have to bring your energy, which is money. So the general principle we'll be looking at time and time again is that when small molecules want to join larger structures, they're the ones that have to bring the energy. So this means that we need to charge the glucose 1-phosphate with energy. We are going to do that with UTP and generate UDP glucose. So the UDP molecule will be on the phosphate on the number 1 carbon. The enzyme that does this is UDP phospho gluco pyrophosphatase. Phosphorylase. This enzyme catalyzes the using the energy of UTP and charges up. So this here is considered a high energy bond. So the conjugation of UDP with glucose now provides the energy for glucose to join the larger molecule. So now we have our substrate for glycogen synthesis. Now a question begins is that the next step is to add this to the growing glucose polymer. And this is going to be done by glycogen synthase enzyme. So glycogen synthase will add UDP glucose in an alpha 1,4-O glycosidic linkage. Recall this is the same linkage that is used in starch. So we will be taking the glucose, UDP glucose, add it to the growing glucose chain. The hydrolysis of UDP off of the glucose will drive the energy for this formation. And so the glucose will be adding from the number 1 carbon to the number 4 carbon of the glucose chain. So if this is our growing chain of glucose molecules, notice these are all in a alpha 1,4 linkage. What we have here is a hydroxyl on the number 4 carbon, and so the UDP glucose will be adding here to form the alpha 1,4 linkage. Now the glycogen synthase enzyme will only work if there's already a glucose polymer. So the initiation of this needs to start glycogenin. And the way I like to think about glycogenin is that it has a very deep active site on this protein, where we are going to now add a glucose residue. This is covalently coupled to the protein. And then the glycogenin molecule has glycogen synthase activity. It is not glycogen synthase, but it has the activity so that it is able to add glucose in a polymer. Now this occurs all in the active site, and this is the beginning of our glucose polymer, the beginning of our glycogen. So once the glucose now extends past the active site, the enzyme within the glycogenin cannot add more glucose because it just can't reach out there. Now is when the glycogen synthase enzyme is able to recognize the growing polymer and continue adding monomers of UDP glucose. Now once the polymer grows to a certain length, say these are our glucose residues, linked together with our 1,4 linkage, the thing to consider is that right now we only have one end. If this is the number 4 carbon, we only have one end of the growing polymer to add to. Well, this is very inefficient, so what we are going to do is hydrolyze an alpha 1,4 linkage, and we are going to take this unit and move it to form a branch structure. So notice that I've drawn approximately 6 residues. So once 6 residues form, then we are going to form the alpha 1,6 branch. And this is done by an enzyme called the branching enzyme. So the branching enzyme recognizes approximately 6 to 8 residues, 6 to 8 monomers that have been linked together in glucose, hydrolyzes the alpha 1,4, transfers this over to an alpha 1,6. What we've essentially done by the branching enzyme then is we now have a free number 4 carbon to continue adding glucose, UDP glucose, and here we have another number 4 carbon. So the purpose of the branching enzyme is to increase the number of free ends. This will increase the density of glycogen. So if we have a long polymer, we have a branch, and another, this can also branch, and etc. We can keep branching these molecules. Effectively, what we're doing is dramatically increasing the free ends to add glucose. Now this is vital to the function of glycogen because we want plenty of free ends to add to, because we want to construct glycogen as quickly as possible in the fed state. And then the opposite, and during the fasting state, when we need glucose released from our glycogen stores, we need to rapidly release it, and now we have plenty of ends to work on.